Hello, my dear students. Welcome back. I know. Your exams are just around the corner and the pressure is really on, right? But don't you worry one bit, because I am here to make it all super simple for you. Today, we're going to smash through the entire chapter on sound in just a few minutes. And hey, if this helps you out, make sure to hit that subscribe button and let me know in the comments.
Okay, let's just jump right in. Have you ever been watching a storm and wondered about this? You see that huge, bright flash of lightning, and then you wait. 1, 2, 3 seconds, and then, boom, you hear the thunder. But they happen at the exact same time. So what's with the delay? Well, this whole chapter is basically a fun little investigation to find the answer to that exact mystery.
So, to crack this big mystery, we need to gather some clues, right? So let's all put on our detective hats. Our very first clue is figuring out what sound actually is. Ready? Let's get started.
All right, here we go. Clue number 1, the fundamentals of sound. Everything, and I mean everything, starts right here.
So what's the most important thing to remember? Sound is a form of energy, and it's always, let me repeat, always produced by vibrations. Just think about it for a second. A buzzing bee, the strings on a guitar, even my voice right now. It's all because my vocal cords are vibrating. It's just a super fast back and forth motion. No vibration, no sound. It's as simple as that.
Okay, detective team, let's move on to clue number 2. So we know sound is a vibration, but how does that vibration get from, say, the school bell all the way over to your ears? How does it actually make that journey?
Well, here's the thing. Sound needs a friend, a dose to travel with. It can't travel all by itself. And this friend is called a medium. A medium can be a solid, like your desk, a liquid, like water, or a gas, like all the air around us. Without a medium, sound is totally lost. It absolutely cannot travel in a vacuum where there's just nothing.
So how does it move through its friend, the medium? Okay, imagine the Delhi metro during peak office hours. Everybody's packed in super tight, right? That's kind of like a compression, a place with really high pressure. Now, think about the same metro in the middle of the afternoon. It's almost empty. People are spread out. That's like a rarefaction, a place of low pressure. Sound literally travels by creating a chain of these high and low pressure spots.
Time for a very important exam question. So, you're on the moon with your friend, and they shout your name. Can you hear them? Think about clue number 2 for a second. The answer is, nope, not at all. And why is that? Because the moon has no air, no atmosphere, basically no medium for the sound to travel through. It's really that simple. You have to remember this.
Okay, detectives, let's get to our third clue. Why does a guitar sound so beautiful, but a car horn sounds, well, like a car horn? They're both sounds, right? It's because different sounds have different properties, a different identity.
Now, the two most important properties you need to know are pitch and loudness. Pitch is all about how shrill or deep a sound is. Think of a mouse's high-pitched squeak versus a lion's deep roar. This is all about frequency. Loudness, on the other hand, is just what it sounds like. It's the volume, how loud or how soft a sound is, and that's determined by amplitude. Please do not mix these two up.
And this diagram shows the difference perfectly. Just look at the waves. See how the top wave has lots of waves packed close together? That's a high frequency, which means a high-pitched sound, like that squeaky mouse. Now look at the bottom wave. See how tall the waves are? That's a high amplitude, which gives you a really loud sound, like the music a DJ plays at a wedding.
Okay, now for the part that you're definitely going to see in numerical problems. This is the magic formula that connects everything. It's super simple. Speed equals wavelength multiplied by frequency. In symbols, we write it as V equals lambda nu, where lambda is for wavelength and nu is for frequency. Write this down, students. Screenshot this page. It is very important.
Let's quickly try a typical exam problem. Don't get scared by the numbers. Step 1, just list what they've given you and make sure everything is in standard units. So 2 kilohertz becomes 2000 hertz, and 35 centimeters becomes 0.35 meters. Easy. Step 2, now we use our magic formula. Speed is 2000 times 0.35, which gives us 700 meters per second. Perfect. Step 3, find the time. We all know that time is just distance divided by speed. The distance is 1.5 kilometers, which is 1,500 meters. So, 1,500 divided by 700 gives us 2.1 seconds. See? You can easily get full marks on this.
And with that clue, our main mystery is solved. The reason you see lightning first is because the speed of light is, well, it's incredibly fast. It reaches our eyes almost instantly. But the sound of thunder, it has to travel much, much slower through the air to finally reach your ears.
And if you need proof, just look at this table. The speed of sound in air is around 346 meters per second. But look at a solid like steel, it's almost 6,000 meters per second. So what's the big takeaway here? This also tells us a very important fact. Sound travels fastest in solids, then in liquids, and it's the slowest in gases.
All right, detectives, on to our final clue. What do you think happens when sound hits a hard surface, like a big wall or a mountain? Well, just like a rubber ball, it bounces right back. And this bouncing of sound, we call that reflection.
Now, here is a key fact for you. A little piece of trivia that's super important. Our brain actually holds on to a sound for about 0.1 seconds. We call this the persistence of hearing. So, for us to hear a reflected sound, an echo, as a totally separate sound, it has to get back to our ears after at least this much time has passed.
And if you do a little bit of simple math, this means that for you to hear a really clear, distinct echo, the wall or the cliff that's reflecting the sound must be at least 17.2 meters away. Both of these numbers, 0.1 seconds and 17.2 meters, are absolute favorites for exam questions, so remember them.
So what's the difference between an echo and something called reverberation? Well, an echo is that single clear reflection, like when you shout your name in the mountains and you hear it back. Reverberation, or reverb, that's what you hear when you sing in the bathroom. It's when you have many, many reflections all mixing together, which makes the sound kind of hang around for longer.
Now, let's talk about something super cool. Did you know that there are sounds happening all around us right now that we humans can't even hear? Yep, it's true. Our ears have a limited range.
As you can see right here on this chart, we humans can only hear frequencies between 20 Hz and 20,000 Hz. Anything below that range is called infrasound, and animals like elephants use it to communicate. And anything above our range is called ultrasound, and this is what amazing creatures like bats and dolphins use to see in the dark and hunt.
And this ultrasound isn't just for animals. It actually has some amazing real-life superpowers that we humans use every single day in technology and medicine.
Just look at this list. Ultrasound is used to clean tiny, delicate parts in electronics. It helps engineers find invisible cracks in huge metal bridges. And in medicine, wow, it gives doctors images of our heart. It can break painful kidney stones without any surgery. And of course, it's used to safely check on the health of a baby during pregnancy. It's a true superpower, isn't it?
So, my dear students, we have solved the big mystery of thunder and lightning and learned so much more along the way. So my final question for you is this. If sound lets us literally see inside our own bodies, just imagine what other invisible worlds are out there, just waiting for us to explore with the power of sound. Think about it. Revise this chapter well. You are going to do great. All the very best for your exams.